So thanks, Tonio, for inviting me to introduce some of the work that we've been doing. So my name's Rob Simpson. I'm from SUTD, which is right next to Changi Airport. If you want to stop by sometime, you're more than welcome. It's the smallest, youngest, and arguably best university in Singapore. My work, I have a group in SUTD. We look at designing chalcogenide materials. These are sulfides, selenides, and tellurides. These are the materials that we're predominantly studying, and mainly for tunable photonics and data storage applications. I want to show you some of the work that we've been doing actually during my PhD, which was quite a long time ago now, and also some of the work that we've continued doing in my group in SUTD. So I just quickly explain what phase change materials are. They are materials that exist in two stable states at room temperature. So here we have an amorphous phase and a crystalline phase. I know your talk at the beginning discussed vanadium oxide. So this is a very famous phase change material as well. It has this metastability and you can switch between the different crystal structures. But this is between an amorphous and crystalline state, and there's a radical change in the properties when these materials switch. So the electrical resistivity changes by a few orders of magnitude, and the reflectance or refractive index increases when this material crystallizes. So more recently, in the last few years, Intel have released Optane memory. Have you heard of Optane memory? So Optane memory sits between the CPU and the hard disk. It's a little bit like RAM, and it's a little bit like a solid-state disk. It's almost as fast as RAM. And the idea is that if you want to store information temporarily but not have access to it as fast as you would normally do with RAM, you'd put it in the Optane memory. So Optane memory is actually based on GST, this famous phase change material. So they essentially exploit this large change in resistance to store ones and zeros, and it can be switched very quickly. But most of the work I've been doing in the last few years has been applying phase change materials and designing new phase change materials for photonics and exploiting the refractive index change rather than the electrical change. The problem is, in the phase change materials community, this is being recorded, so I have to be a bit careful. The development of phase change materials tends to be quite slow. I mean, this material was discovered in the 90s, this most famous phase change material, and there hasn't really been that much done since. It tends to be people doping these materials, trying out different things, using more Edisonian methods, so methods that were developed 150 years ago based on trial and error rather than something a little bit more faster and sophisticated. But during my PhD, these are results from my thesis, I was working with a company called Ilika. I don't know if you've heard of them. They're a materials discovery company that spun out of the chemistry department in University of Southampton. So essentially they use PVD, and by controlling, so physical vapor deposition, evaporation, controlling the rates that they deposit from different angles in the chamber, they can create composition spreads across a wafer. So these are examples of the same sorts of materials that Intel are now using for Optane memory, germanium, antimony, tellurium. We can, this is just a single wafer measurement, we can control the composition over all of these regions. And then we can do very high throughput measurements of the optical properties on the wafer, and then translate it into ternary space. The same is true for sheet resistance here. So this actually shows the sheet resistance in the amorphous phase and the crystalline phase, and you can quickly identify then which materials have a large enough change to be useful for memory. And we also did other things like take X-ray diffraction maps as a function of composition, and then run like principal component analysis to pick out different areas of the ternary space where different crystal structures exist. So that was one way that we were designing materials. I think I liken this to Edison, maybe Edison 2.0, because we're doing everything in one go rather than making samples serially. We make all the samples in parallel, which is slightly more efficient. The other way that I've worked on as a postdoc was creating interfacial phase change materials. Again, the same type of atoms, germanium, antimony, and tellurium, but designing the crystal structure so that we can switch, get an atomic switch rather than an order-disorder switch. And in doing that, we can reduce the set voltage and decrease the switching time for these memory materials considerably. I was also continued working on that when I started my tenure track position in SUTD. But now, more recently I've been looking at a whole bunch of other different design methods. So again, going back to this high throughput combinatorial approach to discovering materials, so creating composition spread films and then mapping the properties. Also using density functional theory and wrapping an evolutionary algorithm code around the DFT code to search for materials with, which are stable at room temperature, and looking for different polymorphs of these structures. And for optimizing these previous structures, these superlattices of germanium telluride and antimony telluride, optimizing the growth. So not only optimizing the design of these things, but also optimizing the growth. I've been using statistical methods, simple statistical methods like fractional factorial designs and those sorts of approaches to quickly identify which growth conditions give the best crystals. Okay, this is just how we sputter these composition spread films. So we have two targets off the axis of the chamber, so we get a composition spread, and then we can map out the properties. And we've developed a bunch of high throughput techniques as well to quickly scan the properties. For instance, this is like an undergraduate research project where they made an array of 144 electrical probes, so we can quickly map out these properties. This is another UROP project where we put the sample on a hot plate, we heat it up and watch it crystallize. The sample has a composition spread. Because of refractive index and reflectivity changes, we can very easily get the crystallization temperature. So here's an example. So we have all of these different crystallization temperatures by just looking with a camera at the material as we heat it up. So in one experiment, we can get something like 340,000 different measurements of crystallization temperature for 340,000 different compositions. So this is what I have been doing. Some of the things that I've been doing. The next steps. So I'm working, as Tonio said, with Mike Short from the Nuclear Science and Engineering Department at MIT. He has a transient grating spectroscopy setup. There are only around 10 of these in the world. There was 9 until the weekend. Then Mike and I built another one. But this allows you to get the elastic constants of materials, thermal diffusivity. And it allows you to get this in seconds, so on thin films. So we're going to make composition spread samples of a range of different materials that are useful for nuclear reactors, which is his interest, and materials that are interested for, I'm interested in some MEMS materials, so new materials from MEMS. And then by looking at these signals from the transient grating spectroscopy, looking at, say, the frequency, we can get the elastic properties, and we can also get the thermal diffusivity very quickly. So within an hour, we should be able to map like a whole ternary diagram with very high resolution. We're also working with Aalto University, Milica Todorovic there. She has developed a code called Bayesian Optimization Structure Search, which is specifically designed for experimentalists to accelerate their optimization. So instead of using statistical designs, which are good for linear trends, we'll be using this other code. And I'm trying to get money now for searching for anomalous materials. So the reason I'm showing all of this to this audience is I think we can create libraries of data very, very quickly. But now I want to start bringing this together with machine learning and trying to infer other compositions that would be useful to look at from the existing library of data, the existing data that we have and new data that we'll take. So that's kind of it. Thank you.